Okay, yeah, so this is a fairly short lab again. So it's just kind of revolving around stents and this new material, nitinol, which I presume some of you are probably a bit more familiar with this than I would be, especially if you're in Trina's lab. So it's just a super elastic material that has a shape memory, and the stress strain curve here that you can see on my screen is in the assignment in the folder for this lab. So basically, we're gonna generate this curve in Abaqus. Okay. Okay, so there is a zip file up. So there's two CAE models in that. So you just download that into your personal folder. So the nitinol example is the second CAE file here. So nitinol uniaxial, and it's basically just an example. So we have a single element here, and we're going to put this through tension and compression and observe the stress strain curve. So if we go in the mesh module, so this model is fully set up. So you can see we only have one element set up here. So that would have been defined in the seeding density. So we have approximate global seed size of 1. And then we can look at the steps just to see what's happening. So we have a loading step and an unloading step. And if you want to, you can take a deeper look at the boundary conditions and loads for each step in the respective step module here. But so this model is fully set up, so I'm just going to run that job. This will just take a minute to run. Okay, that's completed. So we can look at the results. Okay. So now let's plot the stress strain curve. So there's different ways that you can go about doing this. I think we've gone through a few now in the last few tutorials, but I'll just stick with the way that I would normally do it. So go into create XY data. Wherever your XY data is stored, it might be in the history output request, or in this case, it's field output request. Continue. So what we want to plot is stress and strain. So first of all, we have to get our strain data. So let's say we're going to get max principal strain. Okay, and then we just want to select the elements that we want to plot that for. So there's only one element here. So I'll say this set of elements. So that's just one element. There we go. So whenever you're doing this in your analysis, you'll just select the set of elements that you'll want to run this for. Okay, so I'm going to say save, and I'll just plot that as well. Okay, so now that data is stored in the XY data manager, which is here. So you can see all these these bundles of data for each integration point in the element. So if I wanted to export that, there's different ways of doing that, but I would just click on that and click edit, and you can literally just copy and paste that into an Excel file or whatever. And you can plot it from here as well. Okay, so that's strain. So we also need stress. So we do the same again. Okay, so I'll stick with max principal. You need to select the elements again. Okay, save. And that's it plotted. So this is against, so that's like stress against time through the two steps that we have. So now we want to combine the two data sets that we have. So we can go back into XY data and we can go operate on XY data, continue. So here's all our data here that we've saved. And here's kind of functions that we have so that you can kind of operate on these data sets. So I'm going to look for one called combine, and then I'm going to enter in stress and strain. So open bracket. This is expression. Okay, save as strain. Okay, and then I'm going to plot that. So there you go. You can see that's in the same stress strain curve, demonstrating loading and unloading throughout the two steps, and that's the same kind of as we have there in the in our folder. Okay. So then, if you wanted to export that, you could just go into the manager here, and it should be, here it is here. So edit. So I could just literally copy and paste all those. Okay, so that's the first model. So the second model then is a stent. So we'll open up that CAE file. So again, CAE is your entire model. It's called boundary conditions. We don't want to save that. Okay. So in this model, it's fully set up again, and we have a crimper and a stent as our parts. And what you need to do is, I think, let me just open this file up. Okay. Yeah, so we just need to add some constraining boundary conditions. We don't really have to do much. Okay, so we can go into this. I'm just going to hide this crimper. Remove. Dismiss. Okay. So the first boundary condition that we want to add is a constraint around our theta axis. So we want to constrain this face, or sorry, this outer face here, and this inner face here, for theta is equal to 0. So to do that, we need to create two sets, but we can actually do that while we're creating the boundary conditions. Okay, so let's go create boundary condition. Okay, so I'm going to call this end1, and it's going to be displacement rotation. Oh, sorry, actually, I was in the wrong step there, so I was in the initial step. I want to go to the first step. So. Okay, so the first step is crimp. mesh. So I'm creating our set here. So I'm going to call that set and 1. Done. So it says to set, yeah, so u2 is equal to 0. So again, u2 is theta. So in xyz coordinates, it's 1, 2, 3 xyz, and in cylindrical, it's 1, 2, 3 or theta z. So now we want to select our cylindrical coordinate system, which is already defined. Okay, so that's okay. So now we need a second boundary condition on this this face. Same boundary condition. We're going to call that end2. And again, theta is equal to 0. Again, select our cylindrical coordinate system. Okay, that's all good. So secondly, we need a z boundary condition at one end of the strut. So this is seen in figure 2 there, where we need to apply that. Okay. I'm just going to call Z and continue. Select the cylindrical coordinate system. Okay, and then u3 or z is equal to 0. Okay, grand. So yeah, so they have we need to apply like axial symmetry as well. You can read a little bit more about that in the assignment brief there. But I'll just run through it. Okay, so at the non-fixed end, we need to create 2 sets. So tools, set, create. And the first one is called equation set group. It's going to be nodes, a set of nodes. Continue. Okay, so select all these nodes, and then we need to unselect one. Yeah, so we need to unselect this. So to do that, we go back to individual selection, hold the control key, and click this, then left click on that node. Okay, so now that's deselected. So now I can press the middle mouse button. Okay. Yeah. So now we need another set that is just comprised of the node that we didn't select. So tool set, create, and this is called equation set point. Again, it's a node. Continue. And then middle click. Okay, so that's all good. So before we set up this constraint, we just need the ID number of our cylindrical coordinate system. So that should be in features. Right click on this, query, and it's 36. Okay, so now we can go into interactions and set up this constraint. This is going to be equation, continue, equation set group, equation set point. And here is our 36 cylindrical coordinate system ID. Yeah, perfect. So that's actually it. That's our job set up now. We really don't have to do that much here. So I'm going to create that job. Start. Okay. Submit that. Okay, so we just take a minute again. All right, that's completed. So right click on this, results. We can run through the steps. Okay, so I'm just going to hide the crimper. Okay, nice. So the last step then is just a different way of exporting data. I think the way that I did it at the start there is probably easier. The benefit of doing it this way, this new way that I'm going to show you in a second, is just you're exporting the data as an Excel file, or text file, or whatever you want, to a folder. But it's probably just as easy to copy and paste. Okay, so we can go report. Yeah. Field output. We can choose then what step we want. Okay, so pull step, fourth increment. Okay. What we want to export. So let's say again, max principal strain. Okay. And then we can go to setup, and we can set what we want to, like the file name and where we want to export this and so on. So end strain txt, where we want to export it. So select. I'll just choose my folder. Okay. And that's really it. There's some other options here if you can play around with. But yeah, sugar supply. Okay. So we can just look at that file. Here it is in my folder. So yeah, simple as here it is. Then what you can do is you can import this into MATLAB or whatever, and as you can see in the brief, calculate mean stress or alternating stress, or whatever you want from this data. And that is actually it. There's nothing else in this tutorial. There's actually not a whole lot left in terms of anything new to Abaqus. Just look at the final lab. It's probably as short as this was, if not shorter. And we're just looking at one thing. Just again, it's kind of just about interpreting data once you've run your model. So how to extract radial force versus diameter for a stent. And yeah, it shouldn't take long. So yeah, that's it. I know it was a short lab, so I'll just hang out for a minute, or for a couple minutes. Feel free to sign off or ask any questions or whatever.